Geometrical optimization of integral balance for normal and side force using GRA method. Abstract and aerodynamic field. More than 70% of the tests in wind tunnel require some kind of measurement with better understanding of aerodynamic specifications. More efficient aircrafts possible. The force transducer used for measuring forces and moments must be rigid enough to prevent divergence as stability issue and grounding during load path transfer. A 6-component force transducer used for measuring 3 forces: lift, drag, side, and 3 moments: pitching, yawning, rolling, which placed inside a scaled model. An effort was made to increase the rigidity and sensitivity of existing cross-beam flexure sensing element which measures normal force and side force with newly proposed 3 rectangular beams. The geometrical optimization of newly proposed flexure was carried out through Taguchi-based Gray relational analysis. The results showed that increase in sensitivity outputs compared to cross-beam flexure. Introduction. Force and moment measurement is very essential to characterize the performance of flying vehicle for design improvements. The 3 forces: lift, drag, side, and 3 moments: pitching, yawning, rolling moments are the parameters to be studied. To get optimized design, it is extremely important to know all these parameters at initial design phase. The forces measured in model axis later converted into wind axis. The model sting attachment is as shown in Fig. 1. In wind tunnels, to study the performance of the scaled models, such as launch vehicles, satellite, missiles, and aircrafts, a transducer is used for measuring forces and moments. The transducer, generally known as balance, used for measure 3 forces and 3 moments, which later converted into lift, drag, side forces, and pitching, yawning, and rolling moments. Load path starts from model to balance and balance to support system known as sting. For this system to be stable, it should avoid divergence for erroneous experimental results. If there is direct contact between scaled model and support system, then load directly transfers to support directly from model, which results in error reading. Hence it highly demands trade-off between sensitivity and rigidity for designing balance structure. The most common setup for internal balance model is shown in Fig. 2. A complete design methodology of 6-component balance explained. Formulae derived for nominal strain at gauge location and compared with finite element models. To study the balance performance, linearity, stiffness, strain distribution, and interactions were investigated. 1. An experimental study was carried out to determine accuracy of rolling moment element. Rolling moment element was made of 5-bar cage element and compared with a sensitive 1-component transducer. Both of the experimental data were compared for the investigation. 2. Shape optimization of drag force element carried out. Rectangular parallelepiped converted into concave-shaped flexure, and computational results showed that there is a considerable increase in the outputs for concave-shaped flexure with marginal increase in the interactions. 3. Shape optimization of 25 mm internal balance was carried out. The material used for the balance is 17-4 pH stainless steel. Model is prepared in Unigraphics design software and the model imported in HyperMesh software for the meshing and analysis purpose. 4. Geometrical optimization of strain gauge force transducer was carried out. Multi-objective optimization for maximizing stress capacity and reduce volume. Combined Taguchi-based GRA was used to optimize responses obtained from finite element analysis. 5. The balance designed by earlier researchers 1 to 4. There is no mention of using 3 rectangular beam for measuring normal force and side force simultaneously. In this regard, an existing cross-beam flexure was replaced with 3 rectangular flexure, and optimization carried for improved rigidity and sensitivity through Taguchi-based Gray relational analysis. 2. Design requirements and considerations. A. Requirements. The proper structural design of a balance requires accurate knowledge of the design criteria and adherence to these criteria. No explanation is presented concerning the extent to which each of these criteria exerts its influence, because their relative importance depends on the type of balance and the specific objective for which it will be used. In addition, these criteria are not independent, and many interactions exist between them. The requirements and considerations for the design of the balance are listed below. The size of the model is a limitation for the diameter of balance, which cannot exceed 32.5 mm. It is designed for the loads of normal force, N1 1334.4 N. Side force, S1 889.6 N. The instrument should be as stiff as possible, and hence the deflection of the balance with respect to its longitudinal axis should be minimized because it brings in nonlinearity. B. Wheatstone bridge output. Output for the Wheatstone is given by following equation: 1. MV/V, 1. Where K is gauge factor. 3. Structural design of transducer and methodology. The balance has various sections as shown in Fig. 3 and Fig. 4, such as mounting end, grounding end, side force, and lift force. The goal is to fabricate a balance in which the selected section was sensitive in the direction of the considered component and insensitive in the other directions. This objective can be accomplished through the proper design of the sections and appropriate wiring techniques. 4 active strain gauges were used to measure each component of the balance in the Wheatstone bridge circuit. The sectional view of yawing section and pitching section is shown in Fig. 5, and the equations for bending stress is derived using the bending moment equations. Therefore, bending stress at gauge location for normal force measuring element is given by equation 2. Where P, L, M, and N are the sectional dimensions of the lift force and side force measuring element as shown in Fig. 5. The Fig. 6 describes the methodology followed for completing this work and various tools which were employed at various stages of project. After formulating strain equations at gauge location, the geometrical parameters were identified. An L9 orthogonal array is set using Taguchi method for different parameter levels. Based on L9OA CAD models of the balances were prepared in SolidWorks software. These models were imported to HyperWorks software to mesh and carry out linear static analysis for given loadings. The 4 responses obtained from finite element analysis were combined to form a single response with Gray relational analysis, and the optimal parameters were analyzed using Minitab software. 4. Design of experiment and analysis. A. Taguchi design. The 4 controllable geometrical parameters under considerations are L, M, N, P. The chosen levels for each parameters is 3. Hence available orthogonal array for chosen design is L9. The minimum value of L should be equal to 4 mm for strain gauge mounting, and minimum value of M should be 0.5 mm for electric discharge machining. The Taguchi design for 4 parameters for 3 different levels is considered as shown in Table 1, and Table 2 shows number of runs is per L9 orthogonal array formulated in Minitab software version 19. Table 3 and Table 4 contains analyzed data and S/N ratio for deformation and strain at gauge locations respectively. B. Finite element model. The CAD models from SolidWorks software were converted into step files for linear static analysis to carry out linear static analysis in HyperWorks software. The CAD models were imported in HyperMesh software. Balance was meshed using tetra elements with a size of 2 mm for initial runs to reduce the analysis time. After optimization, convergence studies carried out, and element size was taken as 0.5. The results compared with analytical data and difference was 5%. Constraints applied in all DOF at taper region of balance. Loads acted on nodes created at loading station, and these nodes are interconnected to face of balance model mounting end using rigid elements, RB2, similar to calibration loading arrangement for load transfer. OptiStruct solver used for linear static analysis. Hyperview was used to capture the data of stress at gauge location and maximum deformation due to different loading cases. The steps in FEM shown in Fig 7. V result in discussion. Taguchi method is used for optimizations of parameters using signal-to-noise ratio. Higher signal-to-noise ratio means closer to optimal of parameters. It can optimize the single response only and unable to optimize if the number of responses more than one. A. Effect of process parameters on deformation of balance due to N1 loading only. From the Fig 8 it is clear that by setting parameters to level P3, L3, M3, and N3 results in minimum deformation. Parameters N and P are the most affecting. B. Effect of process parameters on deformation of balance due to S1 loading only. From the Fig 9 it is clear that by setting parameters to levels P3, L3, M3, and N3 results in minimum deformation and parameters N is the most affecting. C. Effect of process parameters on strain developed at gauge location for measuring N1 load due to N1 loading only. From the Fig point 10 it is clear that parameter levels P1, L1, M1, and N1 results in maximum strain at gauge location and parameter N is the most affecting. D. Effect of process parameters on strain developed at gauge location for measuring S1 load due to S1 loading only. From the Fig point 10 it is clear that parameter levels P1, L1, M1, and N1 results in maximum strain at gauge location and parameter N is the most affecting. Multi-response optimization using GRA relational analysis. The Taguchi method was unable to optimize multiple responses, hence GRA relational analysis carried out for multiple response optimization. The following steps were followed to convert S/N ratios obtained from each response into collective form. A. Normalization of S/N ratio. The obtained S/N ratio data from Taguchi technique were converted into normalized values using below equations 4 and 5. B. Determination of deviation sequence. The deviation sequence .0 k is the absolute difference between the reference sequence xi0 k and the comparability sequence xi** k, and it is calculated from normalized value represented in table 5. It is determined using equation 6. Values are represented in table 6. C. Calculation of GRA relational coefficient. GRC are calculated to express the relationship between the ideal and actual normalized S/N ratio. The GRA relational coefficient can be expressed by where .0 is the deviation sequence of the reference sequence and the comparability sequence, and .0 equals xi0 k, xi** k, where x0 k implies the reference sequence and 11k. Termed as comparability sequence. Min and max are the minimum and maximum values of the absolute differences, .0 of all comparing sequences. Is distinguishing or identification coefficient in the ranges between 0 to 1. Usually, the value of is taken as 0.5. D. Determination of weighted GRA relational grade. GRA relational grade was calculated by computing average of GRA relational coefficients as given in equation number 8. The overall output response depends on calculated GRA relational grade rank. The values of GRG and ranks represented in table 7. Where x0 xi, the GRA relational grade for the ith experiment, and m is the number of performance characteristics. It is evidently observed from table 7 that GRA relational grade, that analysis number 1 has the highest GRA relational grade of value 1, therefore the first number analysis gives the best multiple performance characteristics among the 9 analysis carried. Ultimately, larger the GRA relational grade, better the corresponding multi-objective characteristics. E. Analysis of variance. The obtained GRG is considered as a single response for designed experiments, and ANOVA was carried out for finding most significant geometrical parameters which affect the multi-objective response. In the present research work, ANOVA is carried out on Minitab 2018. ANOVA is given in table 8. ANOVA calculations are based on F ratio. ANOVA table shows the percentage contribution of each parameter. It is clear from ANOVA table that parameter only n is significant for multi-objective response with contribution of 56.51%, whereas remaining parameters L, P, M contributing 17.86%, 16.51%, and 9.12% respectively are less significant. Using Taguchi method, response table has been generated to separate out the effect of each level of process parameters on GRA relational grade as represented in table 9. Based on the ranking order obtained from table 7 in Fig 12, experiment number 1 is considered best response value. Basically, larger the GRA relational grade, better the corresponding characteristics. From the response table for GRA relational grade, the best combination of the process parameters is set with P1, L1, M1, N1. F results comparison with cross-beam flexures. The cross-beam flexure balance with diameter of equals 31.75 mm and length of 261.20 mm used as reference for studying performance of newly proposed flexure structure. The cross-beam flexure shown in Fig 13. The newly proposed 3 parallel rectangular beam flexures compared with cross-beam flexure of same diameter and material for sensitivity and rigidity due to normal force and side force. The deformation due N1 and S1 load are more than that of crossbeam with increase of 4.72% and 223.36%, which is not desirable, whereas sensitivity, bridge output, for N1 and S1 load increased by 5.63% and 79.18%. 6 conclusions. The aim of this work was to find optimum shape of 3 parallel rectangular beam flexure for improved rigidity and sensitivity. Design of experiment techniques have been utilized for investigation and optimization of selected parameters, in order to get better response. The conclusion based on multi-objective optimization using Taguchi-based GRA relational analysis are summarized as follows. The maximum deformation due to N1 loading is 0.598 mm and S1 loading is 1.48 mm, which are greater than that of cross-beam flexure, used as reference, by 4.72% and 223.36% respectively, which is not desirable. These large deformations for given loading case cause divergence as stability issue in grounding during load path transfer, which results in erroneous results. The Wheatstone bridge output for N1 loading is 1.726 MV/V and for S1 loading is 2.772 MV/V, which are greater than that of cross-beam flexure, used as reference, by 5.63% and 79.18% respectively. Using GRA, the optimum parameters levels obtained in analysis of variance resulted that parameter N has the highest contribution of 56.51%. Parameter N has major influence on sensitivity and rigidity.